Okay, a little bit about setting up for modeling. First, always remember your goal, and especially if you get too deep down the rabbit hole and start to get frustrated, back off. Try and think about what is it I really want to model and what uncertainty do I have. And I'll talk about each of these other topics in this presentation. Okay, what's a year of interest? So this may seem fairly easy at first, but some of you will have data that's a very small number of points. You may need to extend that to a larger area. Some of you, it may be difficult to identify what the area of interest is. I did some gray whale research along the coast of California, and we didn't want to consider the entire Pacific Ocean. So how far out from the California coast do we go? And that was difficult, especially because we had a very biased data set, mostly from shore observations from the gray whales and very few offshore. So, how far out do we go without accidentally cutting off habitat that they could have been in? You also want to know how the area was sampled. Was it rigorously sampled, all of it? Was it randomly spaced plots? Or, much more likely, was it along trails or in some other way heavily biased so that you only sampled a small proportion of the area? If you did it yourself, of course, you'll know these things. If you didn't, you may get data from other folks, especially the worst cases where you get a bunch of data integrated from multiple sources and very little documentation and collection methods. This will happen with data sets like GBIF and bison that have tons of data, often millions of data points for a species, which is extremely valuable, but with little data on how it was actually collected. Also, you want to see how far you can extend the study area realistically. It's dangerous to extend it too far, or in other words, to assume that if you found species in one area and they weren't found outside of it, that's the case everywhere, right? We don't want to necessarily extend it, but we do usually extend it a bit because we need to do that to get good models. So the question is, how far can we do that? And it's always good to pad it a little bit, but again, hard to figure out how far. So as an example, here's Douglas fir in California. See anything that might be an issue? Like that very flat line across the top of the data set? You've probably realized this is Doug fir for California. The range of Doug fir extends way up into Oregon and Washington. And so those are going to be colder in general than California. So we're not only cutting off the range of Doug fir if we stop at the California border, but we're cutting off part of the habitat variability, the coldest areas that Doug fir lives in. So that's going to impact our models, and they're going to be artificially cut off from where they should be because of the extent that we selected. Now, if we want to model up in Oregon and Washington, that's fine, but we need to get some data from there as well. Coastal redwoods, not so much, right? There's a few up in Oregon, but they pretty much end here in California. We'll have problems modeling them for other reasons. Giant sequoia, a good example of where we just don't have much data on them. This is from FIA. There's other data sources for them, but as you can see, there just aren't that many FIA plots with giant sequoias in them. So here we might need to pick a different species because these will be hard to model. Resolution. So whenever we're dealing with raster data, we tend to think higher resolution is better. Especially now we have LiDAR, we have NAPE data for remote sensing at 1 meter. We have UAVs that can get even higher than that. We can get incredible level of resolution. Sometimes this can be misleading, especially if it was from an interpolated source, like most of our weather data is. It can be interpolated from weather stations that are 100 kilometers apart and then interpolated to 30 meters. So that's going to introduce uncertainty that needs to be taken care of and accounted for. Performance problems can also come with high resolution. This happens every semester. And the thing to do there is you definitely want to chop out an area to do your initial modeling in and get things working, and then extend it out to the entire area at high resolution. You can also lower the resolution by just resampling everything. That makes everything go much faster. The problem is that can hide niche environments. In other words, if a species only lives on the backside of boulders or in crevices or narrow canyons, and you go to a lower resolution, those may literally disappear. What happens when we're doing the modeling is that it looks like the species is living in a different environment than it actually is. The recommendation is to use the lowest predictor layer resolution for all layers. So oftentimes we'll see layers at 10 meters or 30 meters. If you have a mix, You would want to downsample them to 30 meters, again being careful that that doesn't take out important information. But you need to downsample them all to the same, and then you run everything at that resolution. Again, we need to remember what we're modeling. So we need a relationship that's going to work, and then we match a method to it. I say measured variables here. I should really say continuous as well. So these are the ones we use the most often as continuous response variables. Height, dBH, canopy size, common in forestry and other plant studies. Weight, length for fisheries, grain size for things like measuring pebble size along rivers, which I've done some work recently. Proportion of one species over another, a dominant species is commonly done, and proportion is actually done in things like disease spread and pollution spread. And income and longevity are common in economics and social science, so this applies in a very large number of areas. And linear regression works for these. And then we tend to move right into GAMs, which we'll do in a little bit. Presence absence, we tend to use logistic regression with GLMs, which we'll be doing soon this week. And they're pretty fun and work really well for this. Occurrences or challenging data set, that's where we just have where we know something is, but we don't necessarily know where it wasn't. So we don't have the absences. And we think we're using point density methods for all of these. That could be a general category for it, but they're also referred to as habitat suitability models or species distribution models. So Maxent being the leading one, and then Hemi being another one that we can use. So sample data. Too many points is going to overwhelm R, and I see this regularly. If you've got 100,000 points, you probably want to subsample that. Just take 10% of it, or take a small area and cut out the points for that and your covariates. That'll allow you to get your models built very quickly, and then you can run it against the whole thing. You can also aggregate them, and in other words, if you could take all the points that are in 1 meter of each other and aggregate those together. That's also a method to convert a presence-absence data set or an occurrence data set into a continuous variable. So many present, so many absent. It also gives you abundance. So different ways of converting your data to use a different modeling method with it. Also, if you have too few points, is it really going to represent the phenomenon like those giant sequoia data that I had? It's just not going to represent the full range of the species. It's not going to give us a good model because of that. So we need to get more data. You could potentially switch to a simulation. We'll talk about that later in the semester. Has its own advantages and disadvantages. Or you could give up, change species, do something different. Just eventually, sometimes you can't build a model for the species you want to right now. When you're looking for predictors, look far and wide. So a lot of times there's a predictor that we want, that we'd love to have. We don't have it. Soil moisture. We really want soil moisture for plants. We don't have it. I think I've once seen soil moisture data, actual soil moisture data for a study. And instead what we have is we have precipitation. So precipitation can be a proxy for soil moisture, and we use it very effectively. It works well. Especially when you link it with things like temperature and then slope and aspect. Suddenly we're able to get a good idea or good indicators of what soil moisture is, and that tends to correlate with which species are dominant and which are doing well in different areas. We also may need to transform the predictors. However, the higher level modeling functions that we're going to use take care of a lot of that for us, except for things like you definitely want to make sure everything's the same spatial reference. You want to use SI units, things like that, and transform them for that. Once in a while, we will still transform things log linear or something like that, often to make it easier to graph them and look at them. Then make sure you investigate what will predict the phenomenon. So you definitely want to look at the natural history side of any species or any phenomenon that you're looking at. Visiting the site, I think, is critical. I've had students go out and say, you know, this plant only grows on the backside of these boulders. Well, that's suddenly a microhabitat situation. So that's important information to say we really need information on the ruggedness of the terrain that the species is in, because that's a factor. If it's flat, it's not going to do well. If it has boulders to hide behind, it's going to do better. Talk to the experts. They'll have that information as well. And they'll often know where species exist that folks haven't collected data on. Again, if we can't get the predictors we want, we may need to switch to a simulation, or again, may need to give up because it's simply not feasible. And I don't want to encourage you to give up, but I want you to know that there's an out there, and if you can't build a good model, don't keep trying to do it. Switch species, switch the question, switch the topic. There's other work to be done, and then we can wait until we have the data we need to go back to that species.